the ring of integers. It's monogenic. It has square-free discriminant. And a little known fact is that if a number field has square-free discriminant, then it automatically has Galois group Sn. And so this is producing lots of degree n number fields with associated Galois group Sn. And the thing to note is that if the height of such an f is less than x, then its discriminant will be at most x to the n times n minus 1. Right? The reason being that the height is a degree 1 homogeneous function, right? Weighted homogeneous function in the coefficients. The discriminant, as we said, is degree n times n minus 1. So if the height is at most x, the discriminant will be at most x to the n times n minus 1. And so if you count all polynomials of height less than x, they're x to the n times n plus 1 over 2 of them, about. And they all have discriminant less than x to the n times n minus 1. So if you take roughly n, right, n times n plus 1 over 2 minus 1, and then divide it by n times n minus 1, you get an exponent of 1/2 plus 1 over n. So the corollary is that for any degree n bigger than 1, the number of isomorphism classes of number fields of degree n, an absolute discriminant less than x, that are monogenic and have associated Galois group Sn, because they have square-free discriminant, it's at least x to the 1/2 plus 1 over n. So this gives the best known lower bounds for the number of degree n number fields with bounded discriminant. And moreover, we conjecture that we actually, if we're only interested in monogenic number fields, in other words, those whose rings of integers are generated by one element, that this actually gives the correct order of magnitude. And of course, all the number fields that are constructed here also have square-free discriminant. As we saw in Lillian's talk this morning, that property can be useful as well. If we drop the if we want to count all number fields of degree n with associated Galois group Sn, we expect that the answer should be greater than x to the 1. This is the best known so far toward that direction. 1/2 plus 1 over n. Any questions about the tape? Sorry? So I think the best known bound was due to Ellenberg and Venkatesh, and this is not too much bigger than theirs. It was around 1/2. So the question is, why do we expect this to be the right exponent for monogenic number fields? Just the method of proof is really counting essentially all polynomials of discriminant x to the n times n minus. I mean, all polynomials of discriminant. How to say? When you're counting monogenic number fields, you really are just counting polynomials. So usually the problems of counting number fields and counting polynomials are very different. But if you're interested in counting monogenic number fields, then it is really essentially equivalent to counting monic polynomials. The only problem is why we're not getting the exact answer is because we're ordering by height rather than discriminant. But standard conjectures say that if you have a polynomial of discriminant at most x to the n times n minus 1, then you expect a positive proportion of them to actually have height less than x. And we are counting everything height less than x. So that's why we think we're counting actually a positive proportion of all such number fields. So that's why we think that exponent should be correct. In fact, we give a conjectured constant too for what that constant should be. Okay, so how do we get at the density of square-free values of this multivariable polynomial, namely the discriminant polynomial? Because how do we get at the density of square-free values? Well, let's start just generally. Suppose we have a general polynomial g in n variables with integer coefficients. We want to get at its square-free values. So to count the square-free values taken by this polynomial, okay, as a standard in sieve theory, we need to sieve away those points, a and z to the n,